Hi everyone. So our speaker today is Renato Renner. He is a professor of theoretical physics at ETH Zurich, and he also got his PhD from Zurich in 2005. And then he was for 2 years as a postdoctoral researcher at Cambridge University, and then he went back to ETH as a professor. And during his PhD already, he revolutionized quantum cryptography. He came up with like a framework for quantum cryptography, which really allows us to understand much better quantum cryptography protocols and compose them and so on. And what's more interesting, he also came up with, he saw that to understand quantum cryptography, we had to understand quantum information theory in a more general framework, where information theory, usually we think about like many realizations of the same experiment over and over again, and that's a idealization, which is not really true, and he found a way of just like really what's relevant in physics when you only have one realization of the experiment or of your sample or your quantum states to make sense of information theory. And since then he has been exploring that, and many other people are exploring this, and he has been working on applications of that to thermodynamics, for example. But in another area of his research is quantum foundations, and he also had many interesting contributions there to understand randomness in quantum mechanics and to understand whether you can complete quantum mechanics to like a bigger theory, what are the limitations of that. And he will tell us something about this today, but whether about quantum mechanics can be true on the large scale.
Okay. Thank you, Fernando, for the nice introduction and also for the invitation. I also found it very nice here that there is this tradition of having lunch with the graduate students. This was really impressive. I'm really excited to see that there are so many students who have a very broad interest, apparently. So today I will talk about some foundations work, as Fernando mentioned, and my approach to foundations is an information-theoretic one, and what that means I will just explain in a minute. But let me first make a bit clear what I mean by the question of the title of this talk. So quantum mechanics is, of course, a theory we tested now since quite a few decades, and we have found that it's an extremely accurate theory. But most of the tests are, of course, in a regime that involves small objects. I'm now not trying to define what I really mean by small, so this should just be regarded as a sketch. But it's still clear that kind of for daily life objects, objects of the size of humans, we haven't usually any tests. It depends, of course, again, how we interpret size. One could say here that, for example, Bell test experiments over distances of meters or even kilometers are somehow, at least in terms of the distance, on a scale that is, for us, reasonably large. But certainly we don't have tests here when we go to larger systems. And in particular, we also don't have tests really involving big systems, like systems that would be large enough to contain, for example, a human. And this will be relevant for what I'm going to say later. So maybe there is an exception to that we don't have experiments here, and this is particularly maybe a relevant remark now, since 2 days, that for gravitational wave detection, one may use quantum entanglement, and one could, of course, regard this, I mean, these planned experiments that use entanglement also as a test of quantum mechanics rather than gravity, and see how quantum mechanics behaves in a curved space-time. But that's just a remark, and I don't want to go further into that. Rather, I would like to kind of focus on the question whether quantum mechanics can be valid on the scales of humans. And as I said, by that I mean essentially systems that would be large enough to contain me, like a lab or so. Now, I'm not an experimentalist, and I'm not going to propose any experiments that we can carry out to test that. Rather, I take the kind of tools that I have access to, which are tools from information theory. And I try to see, and this is a general thing that is now fashionable, to kind of ask the question whether we can use information theory to learn something about physics. And information theory is really, I see it as a big toolbox that allows us to get a new perspective on questions in physics. And there are many examples where it was useful to use such an information-theoretic perspective. So what do I actually mean by an information-theoretic perspective? So this is just one slide, which is probably trivial for any information theorist. It's just there to make clear what I mean by information theory. So this is a typical information-theoretic problem that we have two parties. So in information theory, we often have several parties. like A and B, or Alice and Bob. And the question is, how can they exchange information? For example, A may have made a measurement and know a certain value. And the question is, how, or does another person who hasn't seen the outcome, how could he learn that value? And of course, they would communicate. And now in information theory, we study such communication. Now, we could say this is trivial, they just talk to each other. Of course, information theory looks at less trivial settings. For example, when this communication line is noisy, and then asks, is it still possible for Bob to get reliable information about Alice's output? But the only thing that is now relevant is that information theory is mostly about knowledge we have, and exchange of knowledge, and reasoning about knowledge that people, or I call them later agents, have. And this is the point of view I would like to take when I look at physics questions now for this talk. I want to ask, what information do we have about certain physical settings, and how consistent are different agents who talk about the same physical setting? So now, as I said, I'm not going to propose an actual physics experiment, but you know, in physics we have lots of thought experiments, and maybe it's less known that there are also thought experiments in information theory. And I would like now to, just as a start, tell you about the thought experiment in information theory, which has a priori nothing to do with physics. It's just about some interesting aspects of knowledge. This is a well-known thought experiment. It's also known as the muddy children paradox. I phrase it a bit differently. And it should serve as a kind of an illustration of the approach that I'm later going to take to explore certain properties of quantum mechanics. So what is this experiment? So assume that we have some agents, these three persons here, on a remote island. And suppose that at some point a traveler arrives and sees these people and asks them what's going on this island. And let's suppose he arrives on a Sunday. I just want to measure dates. So he arrives, and these people tell him that they have a very strange rule that governs this island. And the rule is that anyone who knows that she has blue eyes must leave that island on the next day. That's just a rule. I don't know where it comes from. That's a rule on the island. Of course, the people are nice to each other, so they don't tell each other that, when they see that the other one has blue eyes, because they don't want the other to leave. So they don't also see their own eyes, so you assume there are no mirrors on this island, or no one uses them because he would fear to see that he has blue eyes and then has to leave the island. So now this traveler is surprised because he says, okay, actually I see here people with blue eyes. Now, what happens? There's Monday, and the traveler stays surprised because people are there, and there are people with blue eyes. How can it happen that these guys are still there, despite this rule? But suddenly on Tuesday, the two girls with the blue eyes left the island. Now, okay, that's what happened. Let's now go back and see how these different agents, or what was the reasoning of all these different agents that led to that situation. And by the way, I assume here everyone is rational and honest and so on. So this is not a cryptographic setting, although I'm a cryptographer partially, or at least in my past. So when T arrives, he gave apparently kind of useless information, because everyone on this island sees at least one person with blue eyes. So I don't know whether it's visible from the back, but these two girls have blue eyes, whereas she has green ones, but at least each of them sees one other person with blue eyes. So this information is apparently completely useless to them. So how do they, however, reason? So B, for example, sees that A has blue eyes. So she's not worried, and she doesn't need to conclude from this information that she has herself blue eyes, because it's absolutely consistent that she wouldn't have blue eyes, because there's someone else with blue eyes. So she doesn't leave the island, and the same is true for A by symmetry. However, on Monday, let's take the position of A. A now knows that B must know that she has blue eyes. Why is that? I mean, A knows that B hasn't left, and the only reason why B could have, for B to stay, was that she saw someone else with blue eyes. But obviously this girl doesn't have blue eyes, so it must be her. So A concludes that B knows that she has blue eyes, so she must conclude from that she has blue eyes and leave the island on the next day. And the same is, of course, then true for B by symmetry. So now I said before that what this traveler said or told these inhabitants of the island was useless, but this is actually not the case if you now think about it. I mean, he said, someone has blue eyes. This indeed is something everyone knows, but what they learn is something else. They now learn that everyone knows that someone has blue eyes. So, for example, for A, it wasn't a priori clear whether B knows that someone has blue eyes. But because this traveler now says someone has blue eyes, and it's obvious that everyone hears that, A now gets a new piece of information, namely, but this information is about the knowledge of someone else. So what A learns from this statement, and which she didn't know before, is that now B knows that everyone has blue eyes. So you see, this is just to illustrate that in information theory, it can be relevant to know what someone else knows. And we are typically, in this experiment at least, drawing conclusions about others' knowledge. So what this experiment is, thought experiment is supposed to illustrate is reasoning about others' knowledge is relevant, and that information like this one has different layers. It's just the information by itself, but it also has implicit the information that once this statement is made, everyone knows that this statement is true, which changes, in this particular case, the situation and the conclusions that people make. Okay, so this was now not a physics example, but what it already illustrates is one rather trivial thing we are doing in daily life, namely, if, for example, we go back to this very standard situation of A communicating to B, then what does B conclude? So if everyone is honest and A tells me that she saw plus 1/2 in a measurement, then B knows that the measurement outcome was 1/2. But actually, this was not directly implied. To be more careful in view of the previous experiment, what B knows is only that A knows that this is plus 1/2. But of course, usually, we are used to do that. We just say, if we trust each other, so that's why I said this, so if a colleague of mine knows something and I know that he knows that, I promote that knowledge to my own knowledge. I mean, that's what we always do when we communicate, or mostly, at least, when we trust each other. So that's somehow a standard thing. It's also even implicit if I read a memory out or something. I trust that the thing that is represented is actually the thing, so I make such a conclusion. Now, I want to go to physics. So this was just about reasoning, about knowledge. But we can now ask a question about physical theories. And what do I mean by that? We could now ask the following question. So if I have a colleague, Fernando, for example, and he analyzes a physical situation, for example, that one on the table, which I may not completely understand. So Fernando analyzes that. Now, rather than analyzing that situation myself, I could do even more complicated thing and analyze Fernando as part of the system and study how he studies the system. So I would essentially not study the system itself, but I would study how Fernando studies the system. But I could use a certain physical theory to do that. For example, if I believe in quantum mechanics, I could describe the system as well as Fernando as a big quantum system, and then ask the question, what conclusions would he, as part of this quantum system, draw about that situation? And then, when I get a conclusion, I could promote to my own conclusion. So, by knowing what Fernando would get when he applies the theory, and I describe Fernando myself within the theory, I get a certain conclusion that this is 1/2, and then I would say, okay, then the theory actually tells me it's 1/2. So this sounds a bit complicated, but in a certain way, we are doing that even when we do apply maybe, let's say, things in special relativity. So I may take the position of someone else and think about so for example, I want to say something about two particles colliding, then I may think about someone else who is in a different reference frame where the calculation is easier and analyze that situation. And so at the end, I'm talking about the analysis of someone else and promote the conclusion to a conclusion I draw. And of course, I have to be careful then to make the correct transformations and so on. But if it's just a binary question about, for example, whether two particles collided, then I can certainly apply this type of reasoning. The question I would like now to ask is whether quantum mechanics allows us to reason in that way. So is it possible for me to describe a physicist who uses quantum mechanics, but I apply quantum theory to describe that physicist? So this is now related to the question at the very beginning, because if quantum mechanics is indeed a theory that applies to systems as large as humans or as large as agents who can themselves apply a theory, then I should in principle be allowed to apply the theory in that way. So I should be allowed to describe another agent who uses the theory using the theory. That's kind of a self-referencing use in some way. And that's what I would like to study, whether this is possible. So in some way, with the thought experiment I'm now going to propose, I will kind of see whether quantum mechanics is valid here. So for the moment, I will just make that assumption. So of course, this is the assumption we will at the end question. But let's for the moment now make this assumption and assume that I can describe systems as large as typical observers or agents themselves as quantum systems. I can model them with a huge Schrödinger equation and a huge Hilbert space. So by the way, this is, of course, very related to these questions that were already asked 100 years ago about Schrödinger's cat, for example. I mean, if this is the case, then indeed a cat would be in a superposition, which, by the way, doesn't necessarily imply we would see it in a superposition, but it would maybe be in one, according to the formalism. And so, in that sense, this is not a new question. This is, by the way, a picture of the most real Schrödinger cat I could find, because it's actually the one in the street where I'm living in Zürich. And this is a metal cat which has been built in memory of Schrödinger, who lived in the house in the back. So, and the cat is designed in such a way that depending on the light condition, it looks dead or alive. So that's really a nice cat. And if you once visit Zürich as a tourist, so this is the address to visit for every physicist who is interested. You will probably not find any other tourists at this spot. Okay. Now, I should make one note just to avoid confusion in what I'm going to present. So, it has been, so if you assume that quantum mechanics is valid on large scales, then we still are, of course, allowed to describe a system from outside. And this is just what Heisenberg called the cut between the quantum classical cut. So if, for example, I have a measurement of a small particle, let's say a spin measurement, with a device, and then maybe someone looks at the device, and maybe this person or animal communicates the outcome to someone else, then this is a whole chain where at the end this guy gets the information about that system. And we can now ask which part of this whole chain do we need to model within quantum mechanics and which part do we need to describe classically. And what Heisenberg already noted is that in principle, if quantum mechanics is in some way universal theory, or at least a reasonably flexible theory, it shouldn't depend on where we put that cut, because it's completely artificial to say that the measurement device is classical, whereas the spin is not, because, of course, the measurement device just consists of physical components which are themselves described by quantum mechanics. The same may be true for the cat, although it's maybe less obvious. But so Heisenberg said, the result I get from analyzing a system shouldn't depend on whether I make this effort and describe this whole measurement device also within quantum theory and then just describe the process of measuring, of looking at this thing as the measurement process. Or I could even go one step further and include the cat into the whole thing and then just ask what is the observation I make if I ask the cat what she has seen. And the result should always be the same. And Heisenberg, I mean, this is the common understanding that it shouldn't matter. I mean, it would be a big problem if the results would differ, because then for each experiment we do, we would have to define where we put this cut, and we wouldn't even probably know how to make that precise. I mean, of course, it's intuitively usually clear where to put it, because we have kind of an understanding what is large and what is small, but if you really think about it, it would be very hard to define where to put it, and it would also be strange if the results would depend on it. So the understanding is quantum mechanics doesn't depend on that, and as Bell already noted, it also doesn't depend on how intelligent this guy is. So that's, this, by the way, the citation of Heisenberg, which kind of makes that statement. You see, he really said that it should be independent. And I think this is a common understanding which I will now also use in this talk, because otherwise I wouldn't know how to use quantum mechanics. So let me now present another thought experiment, a new one, which, by the way, if you're interested, you can find details in the paper that I wrote with one of my former PhD students, which involves different agents who are reasoning about the outcome of a measurement. And this thought experiment is based on many ideas that are around in the foundations literature, in particular the Wigner's friend thought experiment, but also ideas by Bell, by Bruckner, by Hardy, and by David Deutsch, which are kind of all combined in one experiment. So it's a slightly more complicated thought experiment, but let me build it up from something very simple, which is the Wigner's friend thought experiment. And I will just explain all that with pictures. And so in order just to make sure that the pictures are less ambiguous, let me just assume you have a quantum system, which you could think of as a spin system, which can be in two orthogonal states. And we can also measure that system. And for example, if we measure in the vertical direction, then I could get, here I would always get this outcome and here that. So this is just for the notation, essentially. So Z is a measurement in the vertical direction. So let me start with Wigner's friend experiment, which is a basis for the experiment that I'm going to talk about. So Wigner imagined that there is a friend in a box, and this is actually almost the same experiment as the Schrödinger cat thought experiment, except that the cat is now a human being. But this is relevant for this, because for my thought experiment, this person has to be able to apply quantum mechanics, which is unlikely to be true for the cat. So I assume there's this person in the lab, like Wigner's friend, and we could now ask the question, what happens if this friend gets a superposition of up and down? So I indicate this by a spin to the right. So this is my convention, that this is up and down with a plus in between. And so, of course, the friend would say, I get one of the outcomes. For example, she could get plus 1/2. She may also get minus 1/2, but let's assume she got plus 1/2. Of course, that's what we would expect. I mean, we get an outcome. But we can now ask, and this was Wigner's question that he asked, how would I describe now this whole situation if I take an outside perspective? So Wigner is outside, and his friend is in this isolated lab. What is the state of the lab? And, okay, maybe I should say, I will always in these drawings indicate what people observe by these things or statements they could make. So this person, once he has seen the outcome, could of course make the statement that she saw that outcome. And that will be relevant later. So we now take Wigner's perspective, and Wigner could say, actually, because there was a superposition, because quantum mechanics is linear, we just have a superposition of both situations that could arise. So if it was an up, we knew that it would be this thing that comes up. If it was down, we know it's this thing. But now, because we have a superposition and quantum mechanics is linear and the lab is isolated, this is, of course, just a thought experiment. It would be hard to isolate it, but you're interested just in the fundamental principles here. This would be the situation, the correct description of the state from the outside perspective. So that's what Wigner noted. And this is, I should just emphasize, this is not a problem, because it just means that we have different descriptions of a system, but we have also different cuts. But as long as we're not making predictions about an outcome which deviate, then it's not a problem. So indeed, if we put the cut here, Wigner would just say, this is a huge quantum system, so we have that. For the friend, the cut is here, and he has seen the outcome is 1/2, so for him, it's reasonable to assume that now, at least conditioned on this outcome, the outcome is plus 1/2. But at the end, there are two different statements from two different perspectives, but Wigner cannot say anything about the outcome specifically. He just says from the outside the system is in that state. So there is no specific contradiction. But now I would like to take this as a starting point and extend that experiment. And I will extend this experiment in 3 steps, 3 small steps, which will then give some interesting conclusion, which goes beyond, as I would claim, Wigner's conclusion. So the starting point is the experiment we have just seen. So we have this party, whom I now call F2, because there will be another F1 in a box, and she just measures this particle in the Z direction. So, by the way, if there is something unclear, don't hesitate to interrupt, because maybe it's, it could be that I'm going too fast, but okay, we do this measurement, and now is an idea. I now introduce a small idea by Deutsch, who noticed that in principle, if you had very good equipment, of course that's unrealistic, but as a thought experiment, we could in principle measure this entire lab in a superposition basis. So we could use a basis, a measurement basis, which has as one element this thing and another element this. Now, I don't know how to do that measurement in practice, but if you, Deutsch also suggested that in principle we could think of this whole thing being simulated by a quantum computer, and if we had a quantum computer we could actually carry out this experiment. Anyway, for the moment we just assume that this person can do this experiment, and then he would get a certain outcome. Now I label these two measurement bases by fail and OK. And the reason why I label them like that will be clear later. So this is probably for the moment not clear, but let's just take these two bases. Now, as I said before, the state, according to quantum mechanics of this lab, from the outside perspective, will be such a superposition with a plus sign, because by convention this had a plus sign in between. So with certainty, if quantum mechanics is correct, this guy will observe fail. That's just what quantum mechanics tells us, under this assumption we made that quantum mechanics is valid on these large scales, which is an assumption, of course. So quantum mechanics tells us that, and that we need to remember. So quantum mechanics tells us the outcome will be fail if we measure in this measurement basis, and never OK.
Can you repeat again what fail and OK is?
Okay, yes. So I assume here that so this is now a huge, so from the outside perspective, this whole lab is a huge quantum system. And now I could think of a measurement where, and a measurement is of course described by specifying a measurement basis. And so one element of this measurement basis is this superposition of the lab being in a situation where the guy in the lab or the girl in the lab has seen plus 1/2 and where she has seen minus 1/2. And the other one is just the same superposition with a minus sign. So I can measure, of course there will be many other states because this is a high-dimensional system, but I'm just looking at now these two states, and because this outcome, according to quantum mechanics, will occur with certainty, I don't even need to care about the other states for the moment.
And the way you assign fail and OK is arbitrary?
Yes, so the reason why I call it here fail and OK will become clear later. Actually, the reason will be that we will repeat that measurement until we get OK. But this will never happen so far, but we will see that it will happen as I change the experiment a bit. So OK is just needed as a stopping condition for the experiment. I will need to repeat it until I get OK. That's the reason for this thing. Yes?
Inside the box, it means the F2 measured and saw the outcome plus half, for example, right? This is what you mean by that, right?
Yes, so what this thing means is that this is like the state that this lab would be in if indeed the spin I gave was a spin up, in which case she would see certainly plus 1/2.
But she sees by making a measurement, right?
Yes, this person in the lab does a measurement, yes.
You don't want to make a measurement because you want to keep everything.
Aha, okay, this is a good point. Yes, so now when I talk about a measurement, I should have stressed. So in this view where where I have this movable cut, the notion of what is a measurement is relative to the cut. So let's say for F2, the only reasonable way to describe the system is to say that this is the quantum system that she measures, but so if I describe a quantum system, I never include myself as a system, because I wouldn't know how to do that. So the quantum classical cut that F2 makes is here in between F2 and the system. And so for her, this is a measurement. Now, from the perspective of an outside person who may put the cut here, this is not the measurement. So whether it's a measurement or not is now a relative notion. This is why I essentially had this slide about the cut. So for F2, this is a measurement. For the outside person, this is just a huge unitary evolution, which of course, if you would look closer, would correspond to what's happening is that this information about the measurement outcome is copied into F2's informational degree of freedom. So it will be essentially from a quantum information perspective, be a huge controlled knot operation. But if I trace out the environment here, it's like a measurement. So the notion of a measurement is necessarily a relative one according to this Heisenberg-Katzen. So in that sense, from the outside, this is just a unitary evolution, which doesn't contradict the fact that from the perspective of F2 hasn't access to these degrees of freedom, it's like a measurement. Does this clarify? Okay, thanks. So now I do a second extension. There will only be 3 extensions, so this is the most interesting one probably. So we are now modifying this experiment by sometimes not, so far we always prepared this state. So I said the state is that one and then there will be a superposition. But there may be another person who is preparing the whole thing who first flips a coin. The coin can have 2 outcomes, heads or tails. And whenever it's tail, we do the experiment as before. Whenever it's heads, it's just a spin down that is prepared. Now what I assume in addition is that this coin here is actually not a coin, but let's suppose it's a random number generator, a quantum random number generator. This makes it cleaner. So you could kind of obtain this value R by measuring a quantum system, which has with some probability outcome tails and with some probability outcome heads. Now for technical reasons, I actually need that one outcome has probability 2/3 and 1/3, but that's for the moment not relevant to understand this thing. Now I can make certain statements, and now is the place where the information-theoretic part comes in, because I would now like to analyze what statements can the individual agents make if they just use quantum mechanics. So you should just ask yourself, if you were in the position of this person and used quantum mechanics in the usual way, without any, assuming still that quantum mechanics applies to everything, you would say, okay, if I now know, because you have prepared it, I know that R is tail, then of course I know that the spin was the one from before. So this whole lab will be in this huge superposition I had before, which will result in the outcome fail. That's what we said before. So that was essentially the analysis we did before. We said whenever the spin is spin right, then with certainty, according to quantum mechanics, W is fail. And because this person sees the value R, he can make this statement. He can make the statement, if R is tail, then W is fail. So we make this thing. So here, you see, this person can make a statement. If he prepared that, he cannot make a definitive statement here, because now it could be either okay or fail. But now we could also ask what this person could say. And here it's actually even simpler. If this person got an outcome plus 1/2, which correspond somehow to spin up, then it certainly, this person must be sure it couldn't have been that state that was prepared. Because if that state was prepared, the outcome would always have been minus 1/2. So, in other words, this person can conclude if she sees Z plus 1/2, it must have been the case that R is tail. It must have been this state that was prepared.
So, to have a priori information about how R is assigned head tail.
Aha, yes. Okay, thanks a lot for this question. So I assume that, as I said before, I assume everyone is honest. By this, I also mean, in addition, that everyone knows the total experimental setup. So everyone agrees on this setup. The only thing that is different for the different players here is that they have access to different additional information. Like this person doesn't have direct access to R. Of course, if she knows Z, then she can infer R, but she doesn't see it. Whereas this person sees R and can make a conclusion based on R. So otherwise, they all agree on the setting. So there's no disagreement between them. Now I do the last modification, and this is a modification similar to the one before. I assume that also this entire lab gets measured also in the same kind of type of superposition basis, which has okay and fail. And now for time reasons, I don't want to show also that analysis. I just say that we can now again use quantum mechanics to derive a statement that this person can make. And for the moment, you just have to believe me. If you don't, then I'm happy to explain that to you at the end of the colloquium. But for the moment, just take that as a calculation we can make in quantum mechanics from this perspective. He can calculate that whenever he saw okay, and again, this okay basis is a superposition as before, then she can conclude that the state here must be such that Z is always plus 1/2. So this is a third statement we can derive. And now we have essentially everything in place. So let me just very briefly go back. So we have, after each, so we have made several statements which are all derived from quantum mechanics. This is a statement that this person could derive using her knowledge. This is a statement that is relevant. This is a statement that is relevant for that person. So everyone would agree on these implications, but this person knows Z plus 1/2 and can make this implication if she sees 1/2. And this third statement is a statement that is relevant for this person, because whenever he sees OK, he can derive that this is plus 1/2. So far we have just used quantum mechanics as an assumption, together with, and under the condition that quantum mechanics applies to entire labs, which is, of course, a rather strong assumption, but that's exactly what we want to test in some way. So now let me put these things together. So let's now suppose that X actually got OK. Now what?
Is OK here the minus superposition?
Yes, OK is again the minus superposition, but the only thing you have to know is actually this rule I stated, which can be derived by using that. So I didn't now show how this rule came about, but indeed if you take the minus sign, you will get this rule. So it's actually for the experts among you, it's kind of a similar measurement that is used for an thought experiment proposed by Hardy, whom I mentioned before. So now he can make this statement. And now I write this in an information-theoretic way, because I want to be careful, because I can now not say that W knows that Z is 1/2, because W hasn't seen X directly. But of course, these persons have, so they can communicate. So if A tells W that X was OK, then W can use this statement to infer that apparently A now must also know that Z was plus 1/2. So this is just a logical combination of the fact that this guy tells this guy that X is OK, together with this implication here that A can make. Now we can proceed in the same way, and you see the statement get longer and longer, but they're always of the same type, because now A knows that Z is 1/2, but we also know that 1/2 implies that R is tail. So therefore, W knows that A knows that F2 knows that this is true. So we have this chain of knowledge, and it gets even longer if we combine it with the first thing. So we have just now combined statements, but not yet collapsed them, because that will be another assumption, and we'll be careful to directly do that. So that's just logically combining the different statements we have made. And now we could now use this, and this is why I make this explicit, use this consistency condition that I explained with this island experiment. So I said, what we typically do is to collapse such statements into one. So we just say, if I know that someone else knows that something, then I can promote that to be my own knowledge. So let's now assume we are allowed to do that. So then W knows that this outcome that he sees must be fail. However, what we could now do is to repeat the whole experiment until this happens. And the calculation, which I don't show here, shows that this happens with probability 1/12. So we can just repeat the experiment many times, and certainly after sufficiently many repetitions, this will happen. So we just always start from scratch. We set it up new, and at some point we will have that situation. But now, what we have seen before is that quantum mechanics gives us this long chain, which we can collapse to that. And now, we could also assume that, this is an assumption I also want to make explicit, if the outcome was fail, then it is not at the same time also OK. So an outcome has a definitive value if I see it. I mean, this is kind of explicitly mentioned, because in many worlds interpretations, you would say, OK, it could well be that this value has two values, actually. So I assume here, if it's fail, then it's not OK. But if we make this assumption, we, of course, arrived at the contradiction, because we just said we repeated the experiment until we have this. So in other words, just to maybe summarize, what we have done is we have achieved a situation where these two guys repeat an experiment until they have a particular outcome. Now, based on this outcome, by chain of reasoning, which is just based on conclusions drawn from quantum mechanics, that's why this Q, they arrive at this chain. And if they now assume that they can consistently combine that to one knowledge, then they arrive at the contradiction that they have actually seen the opposite of what they have seen. So something must have been wrong in this argument. Okay, what does this all tell us? Of course, one can make that all more precise. I was now quite sloppy in all these definitions, but I mean, quantum information theory, we are used to essentially try to formalize things, and you can turn this into a theorem, which essentially tells you that one of the assumptions that I've put in must be wrong. So in that sense, I'm not defending any of these assumptions. So the theorem just says one must be wrong. So what were the assumptions? One was, again, that we can apply quantum mechanics to systems around us, which even if they are large. The other one was that if I see a particular measurement, or if I attribute the measurement up to something, then I should not at the same time attribute the opposite measurement to it. That's just assuming that what I see is really the only thing, that I don't miss something like another world in which I've seen the opposite. And then the third thing is that we can do this consistent reasoning, that if I know that someone else knows something, then I can promote it to my own knowledge. So the theorem says that one of these three assumptions is just wrong. So we must give up one of them. So let's now see what that means. Now, if I usually talk to people about this thought experiment, they all have very strong opinions about this. And that's why I put here this last item. And so most people have a very clear, it's clear that Q is violated because there's a collapse or something like that. So now the more neutral position one can make, and I don't favor any interpretation any longer because they all have somewhere a cross, and they have to have a cross somewhere because the theorem tells you that it has to have a cross. But they all have the crosses in different ways, so it's not at all clear. That's what this thing should imply, that where the error is. So there's a huge disagreement in the community. Which is the assumption we need to give up? And I think that's, in a sense, the remarkable thing, that we have quantum theory since 100 years, but this table shows that we have a huge variety of explaining what happened actually in this thought experiment. And I don't now want to go through all these points individually. I just want to remark one. I mean, there are some obvious things, like if you have a collapse theory, then obviously you just violate the assumption that quantum mechanics, as we know it, applies to large systems, because for large systems, this collapse mechanism will become relevant and change things. The other obvious thing is that if you take many worlds, then of course you avoid this assumption that if I've seen an outcome, like let's say head or up, then I've not also seen an outcome down. It's also a bit the question of what I even mean by that. And it's not clear. So there are many, many words interpretations, as I just noticed today when we talked about the grad students. So some of them also violate this consistency assumption. But in principle, the theorem doesn't say that they have to, because there's already a cross here. Okay, one could now have about each of these theories, fill a whole lecture and discuss why this cross is at this particular point. This is really just to illustrate that there is no agreement. So if you tell me it's clear that it's there, then you're just somewhere here in this line, but it's not an agreement among the physicists where we are. So, but what are the options we have? So one option is to give up that consistency requirement. So this is just an illustration of the consistency requirement. You could say, okay, we should just not do that. Whenever I know that someone else knows something, this does, even if I trust the person, I mean, trust means, I mean, this is really the strong sense. It means that I know that if I was that person and I applied the same physical theory, I would have reached that conclusion. But still, even then, I'm not allowed to promote that to my own knowledge. So that would be quite problematic to give it up. In particular, it would, I mean, it's what we always do in science, essentially, and it's particularly relevant in information theory and cryptography. Without such a rule, I wouldn't know how to do any of these statements in information theory. So I personally don't want to give it up, but okay, that's at the end not what the theorem, and the theorem doesn't prefer any of these assumptions, so that's fine. So giving up many words as this other assumption, S, okay, I called it S before, just means you go to a many worlds interpretation. I also don't want to go further into that, but that's one option. That's one way out. We just accept that there's no single reality. So actually, one could even say the experiment we have seen is a specific example where I could So if you are a many worlds person, you could say, this is an example where I could do an experiment, and at the end of the experiment, I can even conclude logically that I've also seen the other outcome. So in that sense, it could see it as something supporting many worlds, but on the other hand, it's not clear that consistency holds in many worlds. And the other option, and this refers to the title of the talk, is to say, okay, this just proves that apparently there is a problem in quantum theory. So if we apply quantum theory to large objects where we haven't tested it, that's the whole point. I mean, we cannot do this experiment. That's why we do this theoretical analysis. But maybe this all just maybe shows that what I presented you, this thought experiment, is not even in principle feasible. Of course, it's not practically feasible, but it would say quantum mechanics is just not valid as a theory on these scales. There is another, we have to look for a different theory. So, of course, one could try to explore this question experimentally, and this is just a graph. It shows that we are far away from doing that successfully. So this is taken from a paper which tries to introduce, and I emphasize the word try, because so there are different measures of macroscopicity or how large a system is. This paper just tries to introduce such a measure, and one can dispute whether it's a good measure. So it's kind of a logarithmic type scale. And you see, one has made progress. So each of these points indicates successful experiments to show that quantum mechanics is valid on this level of macroscopicity, or on a certain size of a system. And you see, we are still far away from human scales, which would be, yes, I mean, you can see, it seems we are not yet there. On the other hand, maybe we are not so far away still, because if we had the ability to build a scalable quantum computer, then we could, in principle, say that even if you have a small quantum computer, but we know it's scalable, then we could argue that it's now just a matter of resources and no longer of a fundamental principle not to have the large system. But this is just a remark which is I essentially make to stress the point that quantum computers are not only interesting for their actual applications in solving problems, but they're also interesting for research in foundations, because if we had a scalable quantum computer, that would prove that maybe quantum mechanics is actually really applicable for very complex systems, at least complex. I don't say large necessarily. So that's my conclusion slide. The question, as I said, was, is quantum mechanics valid on large scales, or here more precisely on human scales? And experiments don't yet give us an answer at all. So we don't know it. We cannot test it at the moment. Now, what theory tells us, and this is what I try to convey in this talk, is that if the answer was yes, so if it was valid, it would mean we have to give up one out of these two very intuitive assumptions, which are not so easy to give up. So either we have to give up the assumption that measurements have single outcomes, so we would need to move to something like a many-world theory, although we don't even have really a good many-world theory. It's just more an idea rather than a theory. And the other possibility would be to give up this consistent reasoning assumption, at least in full generality. So we would then have to look for conditions under which it's still allowed to reason in the way I explained. So in other words, what theory tells us is that there is kind of in some way, high price to pay if we want quantum mechanics to be valid on human scales. But on the other hand, it maybe tells us that maybe nature is really very different from how we experience it in daily life. Okay, that is all. If you're interested in more, you're referred to that preprint, which explains the thought experiment in detail. Thanks a lot for your attention. So this is a very good question. So the question is, is the role of the agents in this experiment? Do we need humans or not? And you see, at the end, it depends on the interpretation actually. So I just say the thought experiment takes agents, whatever you mean by that. Now, in certain interpretations of quantum mechanics, people say that whenever, like for example, in certain collapse theories or in Copenhagen, an agent has actually a role a specific role of saying if an agent measures the system, then there is a collapse or so. So in some way, you just need an agent which, whatever interpretations you have, fulfills this role of being able at the end to apply the physical theory and talk about outcomes. So in principle, you could say that you can replace the agent by a computer which just applies a physical theory. So maybe to just be a little bit more precise, so if you look at this experiment, the only thing the agents do is actually to measure something and make a prediction. And so it's not that they need I don't need terms like they have some experience or so. The important thing is that they can, in principle, be systems that are able to use quantum theory to make a prediction. So in that sense, they don't need to be organic or whatever. So in my opinion, they just need to be information processing systems that are complex enough to apply quantum theory. So the question is really, can objects that themselves are complex enough to use quantum theory be described by quantum theory? So that's...
When you began speaking of these experiments, you mentioned how measurement is relative to where we put the cut.
Yes.
You also made like an offhand remark how an observer who thinks of performing measurement will never put the cut, will always put the cut before them.
Yes.
Isn't that sort of, and you mentioned like, I don't know how I would describe the knowledge with quantum mechanics or whatever. Aren't you then there saying that quantum mechanics does not apply to all the scales if you're always putting, if an observer always puts the cut before them?
Okay, that's also a very good question. So the question is essentially, why do I assume that the observers don't... So for example, if, let's say, this observer makes a statement, he doesn't make a statement about herself, but just about that system, for example. So the cut is outside of the observer. The reason is just that what I want is a statement about quantum mechanics as we use it in... I shouldn't claim that textbooks says that we can apply quantum mechanics to humans, but quantum mechanics says we have a system and we apply a measurement to it, and the measurement is not part of the system. So to even apply quantum mechanics in Born rule or so, I need a separation between a system that is measured and an outside.
But the quantum mechanics is not valid for everything, right? If you're
but no, this doesn't... Okay, yes, so this doesn't now imply that quantum mechanics is not... valid if you apply it from the outside. It just says that one possible way of applying quantum mechanics is that I take myself out of the system. So I don't, maybe I should make clear, I don't claim that it's impossible to include myself. I don't know exactly how to apply the Born rule in this case, so I don't need it for that. But I'm not making that statement. I'm just making the statement what we certainly, so the assumption is only that if I apply quantum mechanics, I should be able to apply it to systems around me, and I don't need to know how to apply it to myself. That would be a too strong assumption that I could apply to myself. So I'm just saying I'm not making the assumption that I can apply quantum mechanics to myself. So I should not be forced to apply quantum mechanics to myself. But maybe that's possible. I'm not trying to exclude that. I'm only assuming that I should be able to describe someone else who uses quantum mechanics myself, which is a different thing from describing myself, because otherwise I would get into loops. Like if I describe myself, is now the description of myself again changing myself and so on. So that would lead to difficulties, which I'm trying to avoid by not making the assumption that I can describe myself. So it's just making the assumptions weaker by saying that. But I'm not claiming that this is not true. Maybe we can do it. And for example, in Bohmian mechanics, it's even necessary to do it according to the general view. They would say you always have to apply quantum mechanics to the whole universe, which includes yourself. So I'm not excluding that, but I don't want to assume it.
I have trouble with your description of the movable Heisenberg cut, because I thought that the bigger the object included within the cut, the shorter the coherence time could be. Practice.
Yes.
Is that a bad way of thinking, or is it that your contradiction applies only if you achieve that perfection of maintaining phase coherence over a long
Yes.
period of time?
I think you're absolutely right. I would also say, of course, for these large objects, we have an extremely fast decoherence time. Now, however, decoherence is always relative to a boundary. And so, if we now move to the situation where we have something in a lab, then the decoherence time here of this whole big object from, I mean, maybe the first thing I should again stress is that the coherence is always relative to what do I define as my system. So if the system is the whole universe, for example, then there's no decoherence because there's just maybe some unitary evolution, maybe, I mean, we don't know that. But if I have now a typical system like a spin or even a larger system, there is a lot of interaction with the outside. So if I define that as a system, there's a very short decoherence time. But now if I say this system is isolated, then by definition, there is no decoherence because I just consider a system which doesn't move any information out of the system. So actually, what I'm saying here is that the decoherence in this thought experiment is by definition no longer there. Now, if I go back to the realistic situation here, this is still true. So, of course, this person would maybe describe decoherence here, but this shouldn't affect the result he gets. So even if he acknowledges that this cat will decohere very, very quickly and therefore kind of become correlated to its environment, the conclusions that are made about the particular outcome should be the same. So the fact that there's decoherence shouldn't change the conclusions that this person makes about that. But I'm happy to discuss that in more detail if this was unclear now.
I have a comment.
Yes?
So it was a good thought experiment. I'm convinced, and this is my personal, because you had one slide that said, what is your personal intuition?
Yes, right.
And I think you need to throw C out the window. And I will justify my intuition by using the Constitution's Fifth Amendment.
Okay.
The US Constitution's Fifth Amendment says you don't need to say anything or do anything that's self-incriminating. So if you go back to your first thought experiment, which had the multi-friend paradox. So if I were one of the people inside living in that city, I would still stay, even though I know that I'm likely to one of the blue eyes, because I'm going to give myself the excuse that the traveler is not to be trusted, and I'm going to stay happily with my friends. So I will invoke the Fifth Amendment,
Yes.
and I'm going to stay.
Okay.
The paradox doesn't exist.
Okay.
And so I'm going to throw out C using the Fifth Amendment. So that's the comment.
Okay, good. That's an interesting additional line that I've never heard about, so I will put it for my next talk.
The question now is, how does this fit into quantum cryptography? Maybe I'm missing that big picture connection.
Quantum cryptography.
Yeah, because you
Aha, yes. So, so this is actually in some way a problem for quantum cryptography, because in quantum cryptography we are always using this. Okay, maybe I should put this here. So in a typical analysis in quantum cryptography, and actually in quantum information in general, I'm typically using all these three things.
Do you use all three?
Yes, we use all three. So in quantum cryptography, I usually assume that quantum mechanics is kind of a universal theory. I even use it actually in a more general sense. I assume the whole universe is governed by quantum. There's no boundary. So that's an assumption in quantum cryptography.
Wouldn't it be irrelevant because your quantum cryptographic systems are not macroscopic?
No, it's actually relevant because in quantum cryptography you analyze a possible adversary. And an adversary, we have no size on the bound on the size of the adversary. So in principle, when we do a cryptographic security proof, we do actually analyze an adversary of an arbitrary size, and so we have to assume that quantum mechanics is now a valid description of that system. So we actually use that in quantum cryptography. Now in quantum cryptography we also use usually consistency, because we have different agents and it doesn't make sense if they disagree.
So my last question is, how do you implement trust in your cryptography?
In cryptography, so I didn't now talk about cryptography.
How do
Yes.
you
Implement it. If I
the
don't.
thought experiment, the fundamental thing is
Uh-huh.
trust, right?
Yes.
I believe
So-
that he believes that he
Yes.
does. How do you, how
Okay, maybe I shouldn't. So the word trust is maybe almost too a bit misleading in this context, because as I said at the end, one should always think of like if someone reasons about someone else, like here, then it's not that maybe it's. I mean, I said B should trust A, but actually what I mean is that B does an analysis of what he did if he was in this position. So it's only trust in some way in your own analysis of, like I could, for example, ask what is this experiment doing from Fernando's perspective, but I now assume that I'm in his position and I'm doing it according to my theory. So I don't really need to trust him. It's more like a way of thinking about what did I do from a different perspective. So it's more taking a different perspective. Yes. Okay, thank you again.
Thank you very much.